So we have been discussing about state models for a system, right? And we had seen that transfer function representation is unique, but there can be infinite number of state models for the same given system. Okay. So as the number of states increases, the number of elements in the ABCD matrix will also be very high. Okay, but which may be difficult to work with practically. So using some standard and accepted procedures, we can have ABCD matrices with minimum number of non-zero elements. So such realizations or models are called canonical forms. So canonical forms are the agenda for the today's lecture. Canonical forms. So suppose we have a state model like this, an nth order system. Okay, we have an nth order system. Say x dot t equals ax plus bu and y equals cx plus d. Okay, it's a MIMO system. That is why there's a bar under u as well as a bar under y. It's a MIMO system. There are multiple inputs, u1, u2, u3, etc., and multiple outputs, y1, y2, y3, etc. Okay, so x is an n by n cross 1 vector. There are n number of states. Okay, let the order of system be nth order system with p inputs and q outputs. Okay, so order of x vector will also be again same n cross 1. What will be the order of u bar? It will be p cross 1 because there are p number of inputs. What will be the order of the y vector? It will be q cross 1. Okay, again x is n cross 1, u is p cross 1. So what is the dimension of A? How many rows and how many columns? N rows and n columns. Okay, n cross n. What will be the dimension of B matrix? There will be n rows and p columns. Okay, n rows and p columns. What will be the dimension of C matrix? There will be q rows and n columns. Q rows and n columns. And finally, the D matrix or the D array will have how many rows? Q rows and how many columns? P columns. It will be q cross p. Okay. So the number of elements in ABCD matrices would be n into n plus n into p plus q into n plus q into p. Okay, which is too large, right? So they can be using accepted practices. They can be brought down into minimum number of non-zero elements. Okay, as I said before, and such a realization or representation is called canonical forms, right? Hence, number of elements in A, B, C, and D matrices is equal to n square plus np plus qn plus qp. Okay, this number is very large. This number is very large and can be reduced significantly by deriving state models using standard and accepted methods. Okay, so such state models with matrices having minimum number of non-zero elements are called canonical forms or standard forms. Okay, they are called canonical forms or standard forms. Canonical forms. Okay, or standard forms. So there are many types of canonical forms. We will be primarily looking into 4 kinds of canonical forms. Okay, so today we'll be looking into the 2 types. First 2 types are controllable canonical form and observable canonical form. So first one is controllable canonical form. Controllable canonical form. Okay. Controllable canonical form, right? So let us take a start with a transfer function. Consider a transfer function. Consider a transfer function. Consider a transfer function say y of s by u of s equals b2 square plus b1s plus b0 whole divided by s cube plus a2 square plus a1s plus a0. Okay, this is the transfer function, right? b2 square plus b1s plus b0 whole divided by s cube plus a2 square plus a1s plus a0. Okay, we are going to derive this in a controllable canonical form. So what I will do, I will multiply and divide this with an intermediate variable w of s. What did I say? I said I am going to multiply and divide with the same with an intermediate variable w of s. There will be no change, correct? So that means b2 square plus b1s plus b0 whole divided by s cube plus a2 square plus a1s plus a0 into w of s divided by w of s. Okay, so in this way, I am multiplying and dividing this transfer function with the same intermediate variable. So there will be no change at all, right? So that means, so now I will do a rearrangement here. Okay, before that, let me draw the block diagram. So this is our u of s, right? Here is a block. Here is our intermediate variable w of s, another block. This is w of s, and this is y of s. Okay. So let me so what I will do is that now I will first enter the denominator part here. Okay, so 1 divided by s cube plus a2 square plus a1s plus a0. Okay, and then I will write the numerator part here, b2 square plus b1s plus b0. Okay, so that means I am first taking this term. Okay, this is my y of s, right? So I can write this as y of s by w of s into w of s by u of s. This will get cancelled, it will remain the same. There is no change at all. Okay, so that's what I am writing here. So I'm just rearranging it, that's all. Okay, now from this block diagram, what's w of s by u of s? W of s by u of s. What is that? 1 divided by s cube plus a2 square plus a1s plus a0. Okay, and from here we will have y of s by w of s equal to what? b2 square plus b1s plus b0. Okay, now let us concentrate on this equation 1. This is 2. So you just cross multiply this thing. What did you get? W of s or s cube w of s plus a2 square w of s plus a1s w of s plus a0 w of s equal to what? U of s. Okay, so in time domain, what does s correspond to? S in Laplace domain is equivalent to what? D by dt, that first derivative in time domain. Okay, so when you convert it to time domain, you will get w triple dot t plus a2 W double dot T plus A1 W dot T plus A naught W of T equals U of T. Okay, so what is W triple dot T from here? I can write, therefore, W triple dot T will be what? Minus A2 W double dot T minus A1 W dot T minus A naught W of T plus U of T. Now I will define, let W of T as x1. Okay, so what will be W dot T? It will be nothing but x1 dot T, which is nothing but x2 T. Okay, up to which point I need to go? I need to go up to W triple dot T. So what will be W triple double dot T? W double dot T will be x2 dot, okay, which is nothing but x3 of T. And finally, W triple dot T will be what? It is nothing but x3 dot. Okay, so I can rewrite this equation in terms of the state variables. Instead of W triple dot, I have x3 dot T. So x3 dot T equal to what? Minus A2 into W double dot is x3 of T minus A1 into W dot is x2 of T minus A0 into x1 of T plus U of T. Okay, what are the remaining equations? X2 dot equal to x3 and x1 dot equals x2 of T. Okay, so if you arrange in matrix form, what do you get? X1 dot T, x2 dot T, x3 dot T equal to what? Some matrix into x1, x2, x3. Plus something else, some B into U. Over here, U is our nothing but, yeah, this is U, right? Yeah, it is into U of T. U of T. Okay, now what is x1 dot? X1 dot is x2. That means 0, 1, 0. So there is no input term, so it is 0. What is x2 dot? It is x3, 0, 0, 1, 0. And what is x3 dot? It is minus A0, minus A1, minus A2, and 1. Okay, so you see here, okay, so we'll stop here. We will wait here. We'll digress from this. Now you consider equation 2, right? From equation 2, what will you get? Y of s by W of s equals what? Y of s by W of s equals what? B2 square plus B1s plus B0. Okay, again you cross multiply. What will you get? Y of s equals B2 square W of s plus B1 s into W of s plus B0 W of s. Okay, or in time domain it becomes what? Y of t equals B2 W double dot t plus B1 W dot t plus B0 W of t. Okay, but what is W? W of t is x1, W dot is x2, W double dot is x3. So we can write this as B2 into, what is W double dot? It is x3. B2 into x3 of t plus B1 into x2 of t plus B0 into x1 of t. So what will be the output equation? Y of t equals, C. What is C here? C will be B0, B1, B2 into x. X is nothing but x1t, x2t, x3t. Okay, so this is my C. This is A and this is B. Okay, if you observe here carefully, you will see that this has a special structure, right? The last row in the system matrix A. Okay, where do you get them from? They are given by the coefficients of the denominator polynomial with all negative signs. Okay, minus A0, minus A1, minus A2, minus A0, minus A1, minus A2. Okay, so in controllable canonical form, always in the system matrix, the last row will be the negative of the coefficients of the denominator polynomial. Okay, and all the above rows in the A matrix will be either zeros or 1. Okay, all the elements in the above rows will be either 0 or 1. And if you see the B matrix, you can see that except last element, last row element, all entries are 0. and the last row element will be always equal to 1. Okay. And finally, if you see the C matrix, you can straight away pull out the coefficients from the numerator polynomial B0, B1, B2. Okay. So this is the characteristic of a controllable canonical form, right? So A matrix will be of this kind. Its last row will be negative of the coefficients of the denominator polynomial. All the above rows will be either zeros or 1. Okay. It will be something like this: 0, 1, 0, 0, 0, 1, and so on. Okay. Similarly, in the B vector, the last row will be 1, and all other elements of the above rows will be 0. And the C matrix or the C array is given by the coefficients of the numerator polynomial. Okay. I hope this is clear to you. So we will write that point here. In system matrix A, the elements of all rows, except the last row are either 0 or 1. The last row contains the coefficients of denominator polynomial with all negative sign. Okay, with all negative sign, right? Coefficient denominator polynomial of the transfer function, that's evident. Okay, then the elements of B matrix are all 0 except the elements of B matrix are all 0 except the last row, which is 1. Okay, then the elements of C matrix are the coefficients of the numerator polynomial of the transfer function. Okay. So let me write here just these things for my convenience. Okay. So x1 dot equal to x2. Then x2 dot equal to x3. And x3 dot equals what? X3 dot equals minus a2 x3 minus a1 x2 minus a2 x3 minus a1 x2 minus a0 x1 plus u of t. Correct? Plus u of t. Okay. Now let us draw the state diagram for this. Okay. In a block diagram shape. Right? So we will start with x3 dot. So you see here, x3 dot is a combination of states x3, x2, x1. Okay, and the input signal. So let this be a summing point, right? So here we have x3 dot. So x3 dot needs to be integrated to get x3 of t. And what is x3 of t? X3 of t is same as x2 dot. Okay, so x3 dot t must be what? A2 minus A2 x3. So here it is coming with a negative sign, and this coefficient is A2 coming from x3, right? So what is significant at this point? It is nothing but A2 x3. Okay, now what next? Minus A1 x2. So you see what is x2 dot? X2 dot is nothing but x3. So x2 dot is x3. So now we need to have another integrator to get what is x2. So this is x2 of t. And what is x2 of t? It is nothing but x1 dot t. Okay. Now you see our x3 dot is a combination of a2 x3 that we have satisfied. Now we need to have a1 x2. So we will take another summing point. Okay. So this is a1 coming from x2. Okay, what signal at this point? It is minus, it is a1 x2t. Okay, now what next? A naught x1. And what is x2? X2 is nothing but x2 is x1 dot. And how will you find x1 from that? You need to have another integrator here to get what is x1 of t. Okay, so x3 dot should have a term coming from x1 at a gain of minus a naught. So another summing point. With a gain of minus a naught. Okay, and plus u of t. So this is the input signal u of t. So I will take a different color to draw the upper branches. Okay. Yeah. So now this is fine. Okay. Now what's the output equation? Y equals b naught x1 t, b naught x1 t plus b1 x2 t plus b3 x b2 x3 t. b2 x3 t. So Y output signal is a combination of all these elements. So that means there should be a summing point here. Okay, whose output will be nothing but y of t. Now, what is y of t? B naught x1 t. So that means here there should be a block B naught. So this signal is B naught x1 t plus what? B1 x2 t. So this is x2. So there should be a block B1 plus. So this signal is B1 x2 t plus what? Plus B2 x3 t. That means this is x3. So here there should be a B2. That should be added here. Okay, plus. And this signal is B2 x3 t. So in this way, we can draw the state diagram for this model. Okay, I hope this is clear. Right? So x1 dot equal to x2, x2 dot equal to x3, and x3 dot will be a linear combination of x1, x2, and x3, as well as the input signal u of t. Okay. Now, as an example, you can try and try a problem. Question: you are given obtain the state space model in controllable canonical form for the transfer function y of s by u of s equals 2s plus 5 whole divided by s square plus 7s plus 10. Okay, you can obtain it. I will give you the final answer. Okay, so x dot, what does this mean? This means x1 dot x2 dot column vector x1 dot x2 dot equal to. So what will be my A matrix? It should be 0, 1, minus 10, minus 7 into x plus what? 0, 1 u. Okay, and what should be y? Y must be equal to what? Column vector. Okay, sorry, row vector. That will be 5 to x. Okay, you can try deriving it for yourself. Okay, so this is what is called controllable canonical form, right? So here the A matrix had the last row picked up from the coefficients of the denominator polynomial, right? And the numerator polynomial will give the C matrix. Okay, and all other entries in this system matrix A will be either 0 or 1. Similarly, in the B matrix, the last row will be 1 and all other rows will be 0s. Okay. Now we will look into observable canonical form, the next canonical form. That is called observable canonical form. OCF. Okay. Again, we will consider the same transfer function that we started with. Say y of s by r of s equals b2 square plus b1s plus b0 divided by s cube plus a2 square plus a1s plus n. Okay. Let us cross multiply this thing. Okay, so what will you get? You will get s cube y of s plus a2 square y of s plus a1s y of s plus a0 y of s equal to what? b2 square r of s plus b1s r of s plus b0 r of s. Okay, I just cross multiplied these between these two terms. That's all. Okay, now I will keep. Now what I will do? I will keep this s cube y of s term on the left side. And I will take all other remaining terms to the right side. Okay, what I say? I said I will keep the highest derivative of y. That means here it is s cube y of s on the left side, and I will take all other terms, remaining terms to the right side. Okay, so I can write like this: s cube y of s equal to what? S square into what? So here we have b2 r of s. So here we will get minus a2 y of s. Okay, then plus s into. Here we have b1 r of s, and you can take this term to the right side. You will get minus a1 y of s plus remaining terms b0 r of s minus a0 y of s. Okay, now what I will do? I will divide both sides with s cube. Okay, so that means our y of s will be equal to what? So here you will get 1 by s into b2 r of s minus a2 y of s plus 1 by s square into b1 r of s minus a1 y of s plus 1 by s cube into b0 r of s minus a0 y of s. Okay. Now we have to define our state variables. Okay. So what I will do is that I will define state variables in this way. Say let x1 of s is equal to 1 by s into b0 r of s minus a0 y of s. Okay. So you see, if x is to be a state variable, then there should be an x dot term. What is the standard form? X dot equal to ax plus blah blah blah. Okay, so if x is to be a state variable, its first derivative should be there. First order derivative must be there. Okay, so you see we have 1 by s, 1 by s square, 1 by s cube. They are all integrators in time domain. Okay, so they all can be defined. They can be defined as a state variable. Okay, so what I am doing is I am considering 1 by s from the last term and the remaining terms here as x1. Okay, and what will be my x2? My x2 will be 1 by s into, okay, so here you see it should be x cube, right? So 1 by s is there already at the outside. So I can write x1 of s plus b1 r of s minus a1 y of s. Okay, b1 r of s minus a1 y of s, right? Now what will be my next state variable x3? X3 of s will be 1 by s into, now you see, I will call this thing, this entire thing as x2. Okay, so x2 of s plus b2 r of s minus a2 y of s. Okay, so you can back substitute and see that this is correct actually. Okay, so here in the first equation you have only one integrator. Second equation you have two integrators here and one integrator here. Third equation you have three integrators here, two integrators here, and one integrator in this expression. Okay, so this is equation A, or I will write A1, A2, A3 to avoid confusion. Okay, now from A1, what will you get? S into x1 of s, that means x1 dot in time domain. Okay, so it becomes x1 dot t equal to what? b naught r of t minus a naught y of t. Okay, now a2, from a2 what will you give? In time domain it becomes x2 dot t equal to what? x1 of t plus b1 r of t minus a1 y of t. And from a3 what would you get? S into x3 of s. That means x3 dot t equals x2 of t plus b2 r of t minus a2 y of t. Okay, so in this way we can derive the state equations. Okay, now what will be our y? Y is sum of all these things. Okay, y is nothing but sum. Y is not y is this term. So that means y corresponds to x3 of s. Okay, y of s means x3 of s. So y of s is nothing but x3 of s. So that means what? Y of t is x3 of t. Okay, now we can arrange it again in matrix. So you see our y of t is x3 of t. So I can write this as, instead of y of t, I can write this as x3 of t. Okay, so here this is x3 of t. This is also x3 of t. Okay, so if you express in matrix form, what will you get? X1 dot x2 dot x3 dot t equal to what? Some matrix A into x1, x2, x3. x1, x2, x3 plus some matrix into U. Now what is x1 dot? Minus a naught x3. So minus a naught x3. All other entries are 0. And here b naught r of t. Or you, what term do we use? R of t or u of t? R of s. So let this be r of t. Okay, b naught r of t. Now what is x2 dot? It is x1 is there. So 1. Then this is minus a1 x3. So minus a1 x3. X2 term is absent, missing. And the corresponding input term is b1. Okay, and what is x3 dot? X2 plus. So there is 1 here. Then a2 x3. So minus a2. And x1 term is missing. The last element is b2. Okay, and what is y here? Y of t will be 0, 0, 1 into x1t, x2t, x3t. Okay, so what happened here? Okay, so let me write the this is what is called observable canonical form. Okay, so parallelly I will write this controllable canonical form also, just for a reference. Okay, controllable canonical form, it will be x dot equals what? 0, 1, 0, 0, 0, 1 minus a naught minus a1 minus a2 into x plus 0, 0, 1 u, and y will be what? Y will be b naught b1 b2, b naught b1 b2 into x. Okay, so you can see here, this is controllable canonical form and this is what is called observable canonical form. So the last column in the A matrix is nothing but negative of the coefficients of the numerator polynomial. Okay, and the input matrix B, what is that? They correspond to the coefficients of the denominator of the numerator polynomial. Okay, and the last entry in the C matrix will be 1 and all other elements will be 0. Okay, all other elements will be 0 here, right? So this B matrix in CCF will be C transpose in OCF. Okay, and C matrix in CCF, controllable canonical form, will become B transpose in CCF. Okay, and A transpose, A matrix in the CCF form will become A transpose in OCF form. Is it not? Transpose means what? You have to change the column. So 0, 1, 0, 0, 0, 1. So sorry, this becomes what? 0, 1, 0, 0, 0, 1 minus A0 minus A1 minus A2. Okay, this is just A transpose. Okay, so if A is the matrix in CCF form, then A transpose will be the A matrix in observable canonical form. Okay, so let us write the points here. The elements in the last column, the elements in the last column of A matrix are the coefficients of the denominator, are the coefficients of the denominator. polynomial. All with negative sign. And the elements of other columns are either 0 or 1. Okay, then the elements of B matrix are the coefficients of the numerator polynomial of the transfer function. Okay, and the last element of C matrix. C matrix means it is a row vector here, okay, of the C matrix or row matrix C is 1, and all other elements are 0. Okay, all other elements are 0. The last element is 1 and all other elements are 0s. Okay, so again, let us try one example here. Okay, so before that, the state diagram we need to draw. Okay, so let me draw it. Let me write these equations here for my reference. X1 dot equals X1 dot equals what? X1 dot equals my B naught R of t minus A naught X3 t minus A naught X3 minus A naught X3 plus what? B naught R. B naught R of t. X2 dot will be what? Minus A1 X2 plus B1 R. Correct? A1 X2 plus B1 R plus X1 plus X1. X1 minus A1 X2. Sorry, minus A1 X3. Minus A1 X3 it is. A1 X3. Okay, minus A1 X3 minus A1 X3 plus X1 plus B1 R plus X1 plus B1 R, and X3 dot will be equal to what? X3 dot is nothing but X2 plus B2 R of t, X2 plus B2 R of t plus, sorry, it's minus sign here, right? Minus A naught X3 minus A1 X3 minus A1 X3 minus A2 X3. Okay, so we will draw the state diagram for this representation. So first we will start with this equation, okay, with X1 dot, right? So X1 dot is here. This is X1 dot t. Okay, so here you will get X1 of t. So X1 dot has an input term, right? So it should be a summing point here, right? So okay, we will come to that later. So X1 dot is what? A naught X3 of t plus B naught R of t. Okay, now so this X1. So what is X2 dot? X2 dot means minus A1 X3 plus B1 RT plus X1. Okay, so it's a combination of these three elements. So there should be a summing point. So because X2 dot is nothing but X1 plus, so there should be a summing point here. X1 T plus what? A1 X3. Okay, so this is X2 dot. Here we should have an integrator. Okay, here we get X2, right? Now, what is X3 dot? X2 plus this thing. So again, a summing point. There should be an integrator here. Okay, so this must be X3 dot, and here we get X3. Okay. Now, what is x1 dot? Minus a naught x3. So there should be a term with negative sign. Okay, I will like this. With minus a naught. Okay, so this should be a naught. From where? From x3. So this is x3. Right? So minus a naught x3. Then what? So what is x2 dot? X2 dot means that should be minus a1 x3. X2 dot should be minus a1 x3. Okay, so this should be negative sign minus a1 a1 x3. And what is x3 dot? X3 dot is minus a2 x3 minus a2 x3. So here is minus and a2 x3. Okay, so now we will look into the remaining terms. What are the remaining terms? There should be an input term. Okay, so if this is b naught, sorry, this is u of r of t. Suppose this is r of t, right? There should be a b naught, say signal b naught. Okay, so the signal input signal r of t is present in x1 dot, x2 dot, and x3 dot. So that means it should come like this. Okay, now at x1 dot, the gain is b naught. So here we have a block with a gain b naught. Okay, at x2 dot, we have a gain b1 r of t. So here we have a block with a gain of b1 plus. And at x3 dot, we have a gain of b2. So this will be nothing but b2 plus. Okay, so this is the state diagram for observable canonical form. Okay, for observable canonical form. Okay, let us try one example. So the same previous example. Okay, I had already given you one exercise. Y of s by r of s, same example equals 2s plus 5 divided by s square plus 7s plus 10. Okay, you can convert it into observable canonical form. So you should get x dot as 0 minus 10, 1 minus 7x plus 5 to r of t. This is A, this is B, this is C. Y equals 0, 1, x. Okay, so you can cross verify. Our A matrix in the observable canonical form will be A transpose in controllable canonical form. Okay, 0, 1, minus 10, minus 7. So if you take the transpose, you will get 0, minus 10, 1, minus 7. 0, minus 10, 1, minus 7. 0, minus 10, 1, minus 7. Right? Then this B matrix, the row matrix B, the column matrix B in controllable canonical form will become what? The C matrix. This becomes 0, 1. Okay, you can see here it is 0, 1 in the C matrix. 0, 1, right? And what? And this 5, 2. The row matrix in the controllable canonical form will become the column vector in observable canonical form 5, 2. Okay, so in this way they are related. Okay, so these are two canonical forms. These are not the only canonical forms. There are many more, and we will see the two more main canonical forms, which are called diagonal canonical form and Jordan canonical form, in the next class. Okay, so in today's class, what did we do? We came across what is called canonical forms. What are canonical forms? Canonical forms are state space models which have the minimum number of non-zero elements. Okay, and we have discussed what is controllable canonical form and what is observable canonical form. So in the next class, we will take up diagonal canonical form and Jordan canonical form. Thank you.